Hi, we are Raptors team from Łódź University of Technology. For 4 years we have been building Mars rover, and this is the latest, the third version. Our group consists of 12 members from different faculties. It can be divided into 4 plus 1 extra group. We have mechanics and designers, electronics, IT developers and PR. We cooperate with the PhD students at the University of Łódź in field of the science analysis. Due to the small number of team members and interdisciplinary character of the project, we perform majority of tasks together, developing and learning in different fields. Our rover is a professional, well-developed construction that can serve as a Martian rover as well as a rescue robot. We have proven this on competitions. We took second prize at World Robot Summit in Japan 2018, as well as 4th and 5th at University of Challenge in USA in 2018 and 17. We are well prepared and we are pleased to compete with other robotics teams all over the world. Hi, I'm Marcin and this is Łukasz, and we are really pleased to welcome you to webinars of Basics of Electronics.
These webinars were prepared in cooperation with Student Scientific Robotics Association Scanner and Raptors team. Raptors team have been building a modular mobile multi-purpose robot for over 3 years. We will start the series of workshops by getting familiar with the basic physical quantities that will appear during the course. It is necessary to understand electronics and move freely in the topic. The basic physical quantities appearing in electrical circuits are current, voltage, resistance and power. Of course, these quantities do not describe all the physical properties of electrical circuits, but it is necessary to understand dependencies occurring in electrical systems. Electric potential. Electric potential is the potential energy of the charge related to its value, or in other words, the capacity of the load to do the work. Imagine a water tank filled with water to a certain extent. Electric potential could be described as pressure generated by this water at the bottom of the tank. The force created by this pressure would make the water flow through the outflow if we open the valve at the bottom. Electrical voltage. Electrical voltage is difference in electric potentials between 2 points. Imagine 2 water tanks connected with a pipe and a valve between them. One of the tanks is filled to a greater extent than the other one. The higher is the water level in the tank, the higher pressure is generated. Electrical voltage could be compared to the difference in pressures in both tanks. Electric current. Electric current is the amount of charge that has flown at a given time, or in other words, the rate of the charge flow. Continuing the situation from the previous scene, if you open the valve between tanks, the water will flow from the tank with higher pressure to the tank with lower pressure. Electric current could be described as the amount of water that has flown from one tank to the other tank. Electrical resistance. Electrical resistance is a measure of how difficult it is for current to flow through a certain substance. It can be compared to a pipe connecting 2 tanks. The longer and the narrower the pipe is, the more difficult it is for the liquid to flow through it. In the actual conductor, electrical resistance is directly proportional to the wire's length and inversely proportional to its cross-sectional area. Resistance of the conductor may result from the number of electrons in this conductor or from the density of the crystal lattice of this conductor. This can be compared to a clogged pipe. The more dirt is in the pipe, or the less water can be found in its cross-section, the slower the water flows through this pipe. Electric capacity is the ability to store charge. This quantity can be compared to a volume of a tank, and the charge stored in it could be compared to a water in the tank. Electric capacity of the element is the amount of charge accumulated in this element divided by the voltage on this element. Power. Power is the amount of work per unit of time. or in electricity, a product of voltage and current. In practice, power tells us how much energy will be processed at a given time. In electronics, the two most important physical quantities are current, I, and voltage, U. While designing, servicing or testing various electronic devices, we must measure these values across the whole system. And that is why we must necessarily learn the basic relations between those two quantities. In the 19th century, German physicist Gustav Kirchhoff formulated two basic laws related to voltage and current, which we will constantly use. Kirchhoff's first law, or also called Kirchhoff's current law, explains how the electric current flows in and out of the nodes in the electrical circuit system. A good analogy would be a flow of two river branches which meet together in a certain point and create a bigger river. The overall mass of the water in the system stays the same. So, the amount of water from the first branch plus the amount of water from the second branch should give us the amount of water in the new branch, which is described in terms of current as the first current, I1, plus the second current, I2, equals to the third current, I3. Kirchhoff's first law states that at any node in the electrical circuit, the sum of the currents flowing into that node is equal to the sum of the currents flowing out of that node. Node is simply a point which connects branches, and current flowing into the node has an arrow pointing towards it. Current flowing out of the node has the arrow in the opposite direction. Let's look at this example. Here we've got 6 branches, of which 3 flow current into the node and current in the other 3 flows out of the node. I1 equals to 0.5 amperes, I2 equals to 0.2 amperes, I3 equals to 0.7 amperes, I4 equals to 0.1 amperes, I5 is unknown, and I6 equals to 0.4 amperes. Let's write down the equation. On the left side, we've got current which flows into the node, and on the right side, we've got current which flows out of the node. I5 is unknown, so let's leave it alone on this side of the equation. So I5 equals to I3 plus I4 plus I6 minus I1 minus I2. With the values we've got I5 equals to 0.7 amperes plus 0.1 ampere plus 0.4 amperes minus 0.5 amperes minus 0.2 amperes, which is equal to 0.5 amperes. Let's consider the same example, but this time current I5 flows outwards the node. So let's write down the equation. Again, on the left side we've got current flowing into the node, and on the right side we've got current flowing out of the node. So I1 plus I2 equals to I3 plus I4 plus I5 plus I6. Now, let's leave the I5 alone on the right side. So, I1 plus I2 minus I3 minus I4 minus I6 equals to I5. Let's write down the values. 0.5 amperes plus 0.2 amperes minus 0.7 amperes minus 0.1 amperes minus 0.4 amperes is equal to I5. Summing this up, I5 is equal to minus 0.5 amperes. This is negative value, which actually means that this arrow should be pointed in the other direction, towards the node. Adding electrical elements to our circuits shows that nodes are as well connections between these elements. So, the overall rules of calculating the currents in this system are the same as in the previous example. What is more, if we've got a series of elements, one after another, the nodes are actually between them. And this kind of connection is called serial connection. Kirchhoffs' second law, also called Kirchhoffs' voltage law, describes how the voltage is distributed among a closed loop. Original statement says that sum of all the voltages in the closed loop is equal to 0. Loops are closed elements of the whole system. In this particular example, we've got two loops, one here and one here, and these are the shortest paths where you don't have shortcuts between elements. As you remember, electrical voltage appears only between 2 points in the system. For instance, here we have a resistor. The voltage on this resistor would be measured between this and this point. Another thing to remember is that on the sources, like voltage source or current source, the voltage has the same direction as the current flowing through the element. And on the other hand, when we have resistors or diodes, voltage has the opposite direction than the current flowing through the element. When we consider sources as the voltage source and current source, the voltages on these elements add up to the overall sum of the voltages in the loop. And on the other hand, on other elements, voltages are subtracted, showing that there are voltage drops on these elements. Here we have a simple loop with one voltage source and two receivers. On the voltage source, the voltage has a corresponding direction to the flowing current, and on the receivers, the voltage is in the opposite direction to the flowing current. We don't know the value of the voltage source, but we would like to have the value of U1 as 5 volts and U2 as 3.3 volts. The question is, what should be the value of the voltage source to provide enough voltage for these two receivers? Here we have a closed loop. Let's write down the equation. Sum of all the voltages in this loop should be equal to 0. So, E minus U1 minus U2 is equal to 0. Let's leave E alone on the left side. E is equal to U1 plus U2. Now with the values, E is equal to 5 volts plus 3.3 volts, which is equal to 8.3 volts. Here we have another, a little bit more complicated example with two anti-serial sources, which means that they are in different directions, and 3 receivers. The first source has a voltage of 20 volts. Voltage of the second source is unknown. The first receiver has 15 volts, the second 12 volts, and the third one is also unknown. Here we have 3 loops. First one, second one, and third one as a whole, and 2 nodes, one here and one here. Okay, so let's write down 3 equations for each loop. Firstly, the direction in which we will sum all the voltages in the loop. First equation will be E1 minus U1 minus E2 is equal to 0. Second equation will be U1 minus U2 minus U3 equals to 0. And the third one is going to be E1 minus U2 minus U3 minus E2 equals to 0. Here we've got only 2 unknowns, E2 and U3, so we need only 2 equations. The third one is an identity and it is not needed to solve it. From the first equation, when we start adding values, we've got 20 volts minus 15 volts minus E2 is equal to 0, which means that E2 is equal to 5 volts. From the second equation, we know U1 and U2. We don't know U3. When we solve this, U3 is equal to 3 volts.
In previous part, we talked about the relationships that occur in circuits between currents and voltages. Now we will talk about the law that is as often used as Kirchhoffs' law. The German physicist Georg Simon Ohm based his work on the conductivity of conductors. He discovered that current is proportional to the voltage, and the element that shows the proportion between current and voltage is resistance. The Ohm's law was formulated in the following way. The current flowing in a conductor is proportional to the voltage applied and proportionally coefficient with the inverse of resistance. Now it may seem a bit hard, but we will learn how to use it. Let's imagine that we have 2 containers full of water. The level of water in the first container is higher than the level of water in the second container. They have different potentials, so there is a voltage between them. Containers are connected to each other with a pipe with a valve. If the valve is closed, there will be no water flow through the pipe to the second container. If we open the valve, there will be maximum flow from the first container to the second. And if we set the valve between the closed and the opened one, we can notice that the water flow is proportional. In our case, the water flow is current, and the capacity of this valve is resistance. Resistors are used whenever you want to reduce the voltage or limit the current flowing in a circuit. This can be shown on LED, which dims when we limit its current. The presented system consists of voltage supply and a resistor. The circuit is closed, so there is a current flowing in a circuit. From the Kirchhoffs' second law, we know that the whole current will be deposited on this resistor. Thanks to Ohm law, we know how big is current. The voltage supply gives us 10 volts and the resistance is 1 kilo ohm, so the result is 10 milliamps. If the resistance decreases, the current will increase, and if the resistance increases, the current will decrease. The next example is very similar to the previous one. but instead of voltage source, here we have current source. In short, current source maintains the constant value, 20 milliamps, of current flowing in a circuit. Attached resistance is 400 ohms. Using the Ohm's law, we can calculate the voltage on a resistor, which is 8 volt. Let us try to analyze more complex circuit. Here we have two voltage sources, each 27 volts, resistor 1 40 ohms, resistor 2nd 20 ohms, resistor 3rd 20 ohms, resistor 4th 45 ohms, and resistor 5th 90 ohms. Our aim is to calculate free current flowing in the circuit, I1, I2 and I3. The first step will be drawing directions of currents and voltages. As we remember, voltage on sources are in the same direction as currents and on receivers are in opposite directions. Now we have to draw the circles inside the loops. In this circuit we have two nodes, so we have to write only one equation from the first rule of Kirchhoff, and we have two independent loops, so we have to write two equations from the second law of Kirchhoff. Now we have to write the equations. Current 1 is current 2 and current 3. And now equations from the second law of Kirchhoff. Voltage on a first source minus voltage on a third resistor minus voltage on a fourth resistor minus voltage on a second resistor plus voltage on a second source minus voltage on the first resistor is 0, and minus voltage on a fifth resistor plus voltage on a fourth resistor is 0. Now I will try to present voltage as Ohm's law. So, voltage first is first current multiplied by resistant third. Voltage fourth is second current multiplied by fourth resistance. Voltage second is first current multiplied by second resistance. Voltage first is first current multiplied by first resistance, and voltage fifth is third current multiplied by third resistance. After all mathematical transformations, we get the result. Current 1 is 0.6 amps, current 2 is 0.4 amps, and current 3 is 0.2 amps. Developing mathematical formulas may seem a little bit complicated, but if we use the rules wisely, we can simplify many elements. Let's recall what combinations of elements do we know so far. Serial connection is called when all resistors are put in a line and end of the first resistor is connected with the beginning of the second. Parallel connection is called when all resistors are connected with both ends. The resistance of the whole set can be calculated in this way. So let's make more complex example now. Resistors second and third are connected in parallel with serial resistor first. First of all, we have to calculate the resistance of resistor second and third, and then we have to add it to the resistance of resistor first. So the whole resistance is like that. Now we can try to look at the connections between resistors and sources, between all elements in the circuit, and try to find other way to calculate this circuit, to calculate the currents in this circuit. First of all, we should try to connect those sources and try to calculate the whole resistance of the whole circuit. Here are step-by-step solution how it should be done. Having total resistance and having one voltage source, we can calculate first current, which is 0.6 amps. Knowing the first current and the voltage on third, second and first resistor, we can go back to those equations and calculate the second and the third current. If one resistor is significantly bigger than the other one in serial connection, we can omit the other one in the total resistance. And if one resistor is also significantly bigger than the other one in a parallel connection, we can omit this bigger one, so the total resistance is only the resistance of the resistor second. The last method is not very popular, but useful. We have to connect the unknown resistor with a known one and a voltage source. First of all, we have to check the voltages on a source and on a resistor. Then, after all calculations, including Ohm's law and Kirchhoff, we know the value of unknown resistance. In practice, sometimes it is necessary to reduce the voltage in a circuit. However, reducing voltage supply isn't possible, and adding a serial resistor isn't the optimal solution. This diagram shows the basic voltage divider. We want to calculate the voltage on the output of the second resistor. When we put voltage to the input of the divisor, the current starts to flow through both two resistors. The current is equal to voltage divided by the sum of those two resistors. The voltage we want to find is equal to the voltage drop of the second resistor. This is the general formula for voltage divider. It is easy to calculate the voltage by multiplying the voltage input by the resistance on which we want to calculate the voltage and divide it by the sum of all resistances in the circuit. However, sometimes the calculations with the voltage divider aren't so simple. Sometimes we have to look at the connection of many serial resistors. Sometimes we may be interested in a voltage such as this marked on the picture. The procedure is the same. Multiply the input voltage by the resistance on which we want to calculate the voltage and divide it by the whole resistance in a circuit. Now we can sum up all the rules which has already been presented. Ohm's law and electric power formula. With all those formulas we can form an electric formula wheel.